So just before we get into the Jupyter Notebooks, I just want to show you some of the fact that with the out-of-the-box functionality of Mathematica, you basically get everything at your fingertips. So if I evaluate this, there we go. So as you can see, this is the number of symbols or essentially functions that you get in newer versions of the software. And as you can see, we're over 6,000 now. And yeah, this should be up to date, so 6188. So we have a heck of a lot of functions available to you. And searching through them is actually pretty straightforward, and you can almost always find what you want because things are named, sensibly. So, obviously like rounds things, tallies things up, sorts things, Same with Python, really. Things are named pretty sensibly. So in this case, rather than writing a function to calculate a prime number, as we did on the previous slide, this function here, which is obviously, it's a pretty poor function and is almost certainly slow and not particularly robust, there's almost certainly going to be one built in. And sure enough, it's PrimeQ. PrimeQ does exactly what you'd expect and tells you whether or not something is prime. And if we just do some repeated computation, so if I do my function and ask whether or not a number is prime and do that repeatedly, so this does it, I don't actually know how many times it does it by default. It'll be in the documentation. So if we just repeatedly run this and then find the average length of time it took to do the computation, it takes nearly a second. So it's a really terrible function. I mean, it's a big number, I guess, but that's very slow. Whereas, of course, the built-in function does it in a microscopic amount of time. So it's almost always better to find a function within the documentation. The built-in function almost certainly does what you want. So in this case, we can ask whether or not a huge number is prime, 10 to the 50 plus 3. And in this case, we can use the documentation. So this is going to open the online documentation here. If I were to search for PrimeQ, then in the documentation, as well as various things about how to use the function, there are always these see also functions at the bottom, which usually give you something helpful. In this case, factor integer, which is what I've used to find all the factors. So apparently, into this composite number, divide the numbers 19, 97, 283, and these ones that are too long for me to be bothered to say. And finally, when you get Mathematica, you don't just get the language itself, you get all of our curated data from the Wolfram Knowledgebase. Sounds very fancy. And this is actually where, if I just grab that, this is actually where the data that powers Wolfram Alpha comes from. So if you've used Wolfram Alpha, as many of you will have done, Wolfram Alpha will find you, will try to answer your question about, whatever. So foot, pound, apparently. There you go. So it's giving me a bunch of information about that. And all that data is stored on our servers somewhere. And it's all curated, cleaned up, kept up to date. And it's all accessible from within Mathematica, so via the Wolfram language. And so in this case, one of the nice things about that is you can either access that data through special functions like, for example, financial data. So this function here actually pulls financial data, from the stock market and has up-to-date data about, in this case, Google, Microsoft, and Apple. Well, you can either do it that way, or you can just ask a natural language query as you would in Wolfram Alpha. So in this case, if I just say discontinuities of this, then it actually outputs Wolfram language code that will do the same thing. So it's quite a nice way of obtaining Wolfram language if you're not that familiar with the language. And in this case, this is actually quite a bizarre example, because this special box here means that this is a function repository function. So I'm slightly digressing here, but the Wolfram function repository is a public resource where members of the public can, submit their own functions. And weirdly, this function here, okay, that explains it. Okay, so I was a bit confused as to why it would pull from the function repository, because that's not a built-in function, but it's because it's made by us. So we can also submit functions, we at Wolfram, as well as members of the public. All right then. So I won't go through the rest of the examples, but I encourage you to look them up, to evaluate them yourself. So moving on to examples. So let's have a look at how the two languages compare with some pretty important aspects of computation. So the first one is integration. So it's a big part of calculus. And in Python, because of course you don't get much out of the box, you need to import different libraries for different parts of the computation. In this case, SymPy for symbolic integration, and NumPy and SciPy for numerical methods, apparently, and Matplotlib. So this is for plotting things a bit like MATLAB. Let's see, PyPlot. Yep, that's another very common one. So essentially, this is all well and good, but it does depend on you knowing about these libraries in the first place. Now, I mean, for many of you, that might be quite an easy thing to do, to find the right library, but for some people it's not. And also there's a question of which libraries are actually worthwhile using. Because they are open source, you can't always guarantee that it's doing the right thing. There's an awful lot of trust on open source libraries, assuming that they will work as intended. And of course, there's an awful lot of trust on the people, who build Mathematica. But they are being paid for it, so stands to reason that they do their job properly. But anyway, so I can calculate that integral, and we get this answer down here. And if I don't lose it, we also get this nice plot here. And I have to say, I am a big fan of these plots, which where the background grid automatically appears as I rotate it. That's quite a nice feature, and I believe somebody may have made a function in the Wolfram function repository that does the same thing. So it wouldn't surprise me if that gets integrated into Mathematica at some point. So that's how you do it in Python. And I will discuss this special cell in a minute, because you're probably wondering how I'm running Python code in Mathematica. And this is how you might do it in Wolfram language. So obviously, because we don't have to import any libraries for the actual integration or for the plotting or anything like that, obviously the code is a lot shorter. And if you're a mathematician, it's especially easy to read as well. It does exactly what you would do if you were to do that integral yourself by hand. You literally integrate this with respect to x. And we can plot, do the same plot. And there you go. Default settings, not especially pretty, but of course you can add all the options you like. I will say one quite nice thing about Wolfram language is that because it's all symbolic, this here, although it looks like it's sort of like the traditional form, this actually can be calculated with. So that's just a nice feature. So if you are writing any notes for students, for example, and you input some maths in line with some text, then the students can just copy it out and work with it. So it's really neat. So that's integration. How about something like letter counts in core language? So we're talking about things like length, map. It might have some threading or zipping, whatever you call it. And all this stuff lends itself to anonymous functions. At least it does for me, coming from a functional sort of language. I would certainly think about using a lambda function here if I were to write this in Python. But anonymous functions in Python are fairly limited. But if you were to write it in the Wolfram language, you'd probably do it something like this, where this function here is completely arbitrary. It can be anything you like. So, if I pull this out, this function here, let's see. Just checking it works. Okay, so this function here, I happen to have given it an argument called string, but I could have any number of arguments here I like, And in fact, I could write this as the shorthand, that if I can find the right key combination, it's not that. I can't remember what it is on Windows. There we go. So we can also do something like this and do string length of something and a little ampersand. And this is a shorthand way of writing the same thing. So, I mean, actually, in this case, you can be even shorter. I mean, you don't actually even need that because it's just a very, very basic function. But, you know, it's the great thing about Wolfram Language is because it's functional, things like anonymous functions are, you know, it's designed for that. So it actually works with them really, really well. And as I mentioned, it's a symbolic language, so you can pretty much chuck anything you like in there and it'll probably try something. In this case, it's trying to multiply two images. And because these underlying are, you know, matrices underneath, I guess it performs some sort of dot product and attempts to convert that back to colors. I don't know. But yeah, it's quite nice that that can be done. For my next example, let's do a bit of maths. Let's do some actual piecewise functional programming. So a big part of a lot of languages are branching functions and loops. And loops especially we don't use loops at all in Wolfram language. I mean, very, very rarely. In other languages, you'll see a function like for. This is probably the least used function in the language. Nobody uses it. We do use things like, well, speaking of looping, we would use something like do or table, or you might do a bit of nesting, so a bit of recursion in there with nest, something like that, or fold maybe. You know, we do have functions for this, but for the actual function for is a no. And in terms of branching functions, we use things like if, while, switch, all of which may be familiar to you, but we don't use them as often as you might do in something like Python. And what we tend to do instead is overload functions. You know, again, we are a functional language, so functions are our forte. So in this case, if we were to write this piecewise function in Python, where this function f does something different depending on whether x is positive, even or odd, or negative. Well, in Python, you might do it like this. You might say if it's greater than 0 and it's equal to 0 mod 2, so it's even, then return the square root of that plus c. Again, we're having to import math here, but that's not really a big deal. Otherwise, if it's positive and odd, we do this. Otherwise, we raise an error. So again, you know, that works fine, although in this case, the error does not translate perhaps quite how you might imagine into Wolfram language, but we'll cover more about that later. But in Wolfram language, although you can, of course, copy this exactly, we don't really do else if. We tend to use something like, I don't know why I used while there. I meant to use which. We would tend to use which there. Instead, we do this. So this is going to look a little bit messy in this particular case, but it is really powerful stuff. And what this one is actually doing right now is overloading the function myfunc1 to say when it takes an input that is even and greater than 0, and the second argument is irrelevant apparently, then take the square root. If it's odd and greater than 0, then take the square root and minus c, and then otherwise output a message of a particular error message stated here. And this is actually, although initially it looks kind of a bit messy, it's actually clearer to another programmer because you can see explicitly this must be even and positive. This must be odd and positive. This must be anything else. And already to me, that is, that is saying, oh, so that means I could put anything in the second, like in the first argument here. I could put an image if I wanted to. So that's already raising some flags for me to say, actually, this function could be improved even further. Whereas here, I have to actually hold all the previous statements in my head to determine, what the current state is. So this explicitly says in the first line, greater than 0 and even. Whereas in the second line, there is nothing to say it has to be odd. That's implicit. That's implied by the fact that it's not even. And we're lucky in this case because, you know, if it's not even, it's odd, right? Well, what about 3.2? Is that even? Is that odd? You know, doesn't make any sense. In fact, what does happen if I do 4.1? And I get a failure. There you go. So it's not completely obvious what will happen in this particular function, whereas in here, it ought to be. So if I evaluate this, of course, I get the same results. Now, I did mention that this was already raising some flags to me, so this actually should output the error as expected, I believe. Yeah, because anything that doesn't fall into here must therefore fall into here. But for me personally, I would actually add an extra condition to say, what if it's not even or odd, and it's not just anything at all? But anyway, that's just a sort of side note about, you know, functional versus branching. So how about classifiers? So this is quite a big one these days. So machine learning, obviously things like ChatGPT and DALL-E came out recently, and, you know, massive deal all over the news. And I'm not saying you can do that sort of stuff very easily yourself in either language, but nevertheless, I want to demonstrate how they, you know, how they compare. So in Python, there's scikit-learn, and which is the big one, I believe, for doing things like machine learning. And obviously, there are these other particular libraries that you can use to do various things. So OS will help you do some file structuring, things like that. But the fact is, it's quite long code, and it's not necessarily that readable. I'm certainly not finding this terribly easy to read to see what it actually is doing, although, of course, there are some comments to help me. And this is the output. It's not particularly pretty. So I'm sure there's a library for that to, you know, to output it in a nicer form. But, you know, generally, it's not the easiest thing to do. Whereas in the Wolfram language, one area where we actually shine is in machine learning, simply because all of the layers in a neural net, for example, are symbolic. And if you want to do a sort of, you know, if you don't understand, say, too much about machine learning, then we also have these high level functions that'll do everything for you really, really easily. And I mean really, really easily. So for example, if we have the same, I believe it's the same data set, yeah, about the Titanic. So in fact, why don't I have a look at that data itself? So you should have this data as well. And I'm just going to open that up. So that's what it looks like. So a bunch of people who were on the Titanic. They've got a class, first, second, or third, and an age as a decimal here. I guess that's a baby, and male or female, and whether or not they survived. And in this case, if I import the CV, I can import it not only as comma-separated values, but also as a special data set, which means it comes out as this dataset object. So just in case you're not familiar, you can create something like this yourself with the dataset function. And so already the output looks really nice, but this is where we really shine with classify. You literally do classify of your data and say what it is that you want to classify. And in this case, we want the outcome based on the class, age, and gender. So I run this code, and I know, you know, it might be that I know nothing about machine learning, so it does all this automatically. I don't need to know anything about it. And it used logistic regression by default, so it's all automated. So I say by default, I mean that will depend on the data that it takes in. And you know, it's literally one line, one very, very short line of code. And now I can use it to make predictions. So given my classifier, I can say, what if there's somebody who is in third class, 23 years old, and they are male? What are the probabilities that they will survive or die? In this case, there's a nearly 90% chance that they died. And if I make them female, I imagine, there you go, much higher chance that they survived because of the whole women and children first. And What you can also do, although I wouldn't, well, there's nothing. Basically, if you want to do some classification and you know what you're doing, you know actually the best method to use here is something else. Well, you can actually tweak that. I'm not saying it's not it's not completely a black box function, so you can do stuff like this. But yeah, I'm not saying you can dive deep down into how it's doing all of its classification, but there is at least some sort of tinkering that you can do to change the outcome. However, of course, in this case, this is actually a pretty bad method to be using. And so if I evaluate this again, it's given me some different results. I don't know whether or not that's a good or bad thing. But if I change this age to something else, well, nothing happened. So I'm guessing this is basically a flat line. It doesn't matter what you put in here. It's probably going to give the same probabilities out because it's just a poor model. So I'm going to rerun that first line there just to make sure that we've got a nice classifier for later. Okay. And I can find out information about my classifier as well if I want to. So use the random forest method. It's given me the details about that as well. Accuracy, not a very high accuracy. There's not very much data, but then again, that to me would be a red flag. For example, if this were a model I was going to be using on real world data, that's not a very high accuracy. You can delve into it as much as you like.